So, yesterday we were looking at basically the elastic buckling stress for tubular cylinder subjected to hydrostatic pressure. The geometric parameter which is defined as basically the ratio of length to diameter multiplied by square root of 2d by t, which gives you an indication that how is the relative size of the member with respect to the length that is going to affect the hydrostatic pressure and associated local buckling. Now, this FHE is basically in the elastic stage, which could be potentially larger. As soon as the elastic stage is exceeded, then it will form a wavy form, which the allowable stress will come down. That is why you see here, the elastic part, especially related to buckling, elastic buckling will be higher stress, elastoplastic will be going down. So, basically we need to find out using the elastic stress, you find out the elastoplastic or inelastic buckling, which will be lower than the elastic stress. The reason why we find the elastic is initially any member against buckling it will be very strong. Once you start a over buckling or basically the waveform, then it starts give away very fast. So, that is why you might normally understand most of the time we have elastic and elastoplastic in the linear bending, basically our tension you normally see the elastoplastic is higher than the elastic, whereas here is exactly opposite. So, the elastoplastic stage you will see that the allowable stress or the capacity will be lower. So, basically you find out the elastic stage using the buckling coefficient CH, which is defined as 5 or 6 stage equation relating to the geometric parameter, which is defined as m, and this m initially if you do not have a rings is the length of the member between the supports, and you start providing rings, then that will become the spacing between the rings. So, it is basically trying to. So, as soon as you have the reduced m value, which as less as 1.5 or less, you could see that the coefficient of buckling or elastic hoop buckling becomes 0.8, and then you start increasing, you could see that the value goes very small. That is what we saw in this particular graph. Basically it reduces very drastically vertically down when the geometric parameter exceeds 1.5. As soon as you reach somewhere around 5 itself, it reaches the value of 10%, you can see here, but after that it becomes very flat. In fact, if you look at this graph, what I wanted to demonstrate is basically the difference between the d by t ratio of 20 and d by t ratio of 60. I have just put two graphs. You do not see any difference when the m value is lower, basically from 0 to probably 10, but there is a small value that actually has some effect on the CH coefficient, but otherwise I think mostly the CH value is independent of d by t, predominantly it is dependent on the length to diameter ratio. So, once you find out this elastic, then you can go back to the elastoplastic, which is basically called critical hoop buckling stress. This is the one that we are going to use for as a allowable buckling stress against hydrostatic collapse. So, basically you find out the applied hoop stress using the formula PD by 2T, compare that with this critical hoop buckling stress. As long as the critical hoop buckling stress is higher, remember this is not allowable stress, we have to find allowable stress from here. This is buckling stress, we have to divide by a factor of safety which can be defined. So, just we are going to look at that aspect, just do not look at the top portion, look at the bottom one. We have got a factor of safety defining the basically the 4 combination of stresses that is going to occur. So, if you look at the last one is the hoop compression due to external hydrostatic pressure. A factor of safety of 2.0 is required for normal situation, and a reduced factor of safety of 1.5 is acceptable when a storm cases storm waves are subjected to. So, basically when you calculate the critical hoop buckling stress divided by a factor of safety of 2 will give you the allowable hoop buckling stress, which you will compare with the applied hoop buckling stress or applied hoop stress of PD by 2T. The table also gives you additional information regarding factor of safety related to basically the combination of hoop stress with other loads, axial tension, bending and axial compression. So, you can see here a typical factor of safety of 1.67, which will yield about 0.6 as the allowable stress. So, basically tension and compression basically is a similar 1.67, but actually the code gives you a range. If someone wants to have a slightly increased factor of safety to have 2.0, but minimum is 1.67, and for bending the ratio of Fy divided by the allowable bending stress, which you already have calculated, can be taken as, again you will get into same like 1.67. For storm, basically you have a slightly reduced factor of safeties, very similar to our normal condition like storm versus operating, we have basically 1.67 and increase the allowable stress by 1.33. You can see here the same thing only we are doing in that particular case. So, basically slightly higher risk is taken for storm waves, or normal situation is basically a reduced factor of safety is not allowed. Now, you see here previously when we look at, I think yesterday only we were looking at the combinations, in these 4 groups of combinations we had axial stress combined with bending stress in all situations. Only thing is slightly different scenarios were taken, the general case, and then where you have reduced or smaller axial load, and this one is slightly higher axial load inducing additional magnification of moment, and the last one asymmetric sections where the bending in x and y directions are different. Now, this is only combining axial loads and bending loads. Now, what we are going to just quickly look at, when you have the stresses arising from hoop stress and bending and axial, because the hoop is added. For example, you have a cylindrical structure, when you have a tensile force as well you apply the hoop stress coming from the hydrostatic pressure, it is going to add problem. And if you have a compressive force and basically you have a external hydrostatic pressure, it actually helps us. So, basically you can see the interaction is going to be slightly different, and the stress direction is 90 degrees, axial and bending in the same direction, whereas the hoop is going to be the in the different direction. So, basically we need to see how the interaction, it is not going to be a same linear interaction what we had Fa by allowable axial stress plus, we are not going to do that. Basically you can see here is a nonlinear interaction, A square plus B square plus 2 times the Poisson ratio multiplied by AB. So, this is the interaction formula proposed in the API code, and we need to calculate the coefficients A and B using this combined stress formula. So, the A is basically the ratio of Fa plus Fb minus half the hydrostatic stress, which you calculated using Pd by 2T, basically the hydrostatic pressure multiplied by diameter divided by 2 times the wall thickness, and corresponding allowable stresses factor, basically S of x is given here, if it is tension is this, if it is compression is this, and then the B factor is a pure ratio of Fh divided by Fhc. This Fhc is the one that we just now calculated here, basically the critical buckling stress due to hoop. So, you take that is the allowable buckling stress, because you have a factor of safety applied there. So, basically that is the idea. So, once you know A and B, you can substitute into this equation, including the factor of safety is defined for axial, basically the whether it is axial tension or axial compression, and basically the the hydrostatic is divided by the corresponding the buckling stress calculated in the earlier step multiplied by the associated the factor of safety. So, you could find this factor is less than 1, then the combined effect of axial tension or compression plus bending plus hoop stress is safe. In any case, we need to make sure that this also separately checked, basically the direct proposition of applied hoop stress divided by critical buckling stress is producing a factor of safety of minimum 2. So, that is the most important, that this factor of 2 must be achieved independent of before you go into the interaction. Interaction is basically a combined effect, of course, yes, but as long as if you can satisfy this, probably you will get this also automatically. And basically that is tension, then axial compression slightly modified formula. So, here you see Fa plus half hydrostatic pressure divided by Fxc, which we just calculated in the earlier stage, this is member buckling. So, you should remember the difference between 4 parameters we discussed also yesterday, Fxc, Fxe, which is corresponding to member buckling due to axial load, Fhc and Fhe is the hoop buckling due to hydrostatic pressure. So, this you should not get confused, in fact sometimes you get a confusion why this is coming here, because here the axial compression is going to create problem for basically the axial load. So, that is why you have the allowable the axial buckling stress, and then you combine with the FB, which is the bending stress divided by the yield, and must be less than 1. This is one formula. The second formula is the direct checking of hoop, basically hoop stress, applied hoop stress divided by allowable hoop stress, which is basically the critical buckling stress divided by factor safety. So, when you divide it, it goes up. So, it is a simple idea. And then the third formula, basically whenever the FHA is greater than 0.5 Fx, which FHA is defined here. So, it is just a sequence of checking required to make sure that both compression and tension effects are checked with respect to combining hoop with the axial loads. Most important is the tension will create more problem, compression may actually cancel the effects, because when you are trying to do this, the cylinder tries to expand, whereas the hydrostatic pressure is trying to act opposite. Now, this Fxc and Fxc, this is what I was mentioning, this is coming from the previous check for the member, not just the local hoop buckling stress. So, you should substitute the right terms, otherwise you will get into big problem. Now, before going to the ring, I just want to show you one table which you will realize this is one of the just a simple spreadsheet. Normally, when you try to say design means you need to have right parameters selected for the particular aspect of design. That means, this particular case we got multiple answers. The loads are given, basically the moment and the applied axial load is given to you. Now, you got see here, we could work out many different types of answers of combinations of diameter and the wall thickness, and in this case we started with say typically 600 as the minimum diameter. Maybe you might be given a range of diameters to work with, you should start like that. Now, when you have a 600 starting point, you can see here the last one, I have just programmed the whole equations what we discussed for the last 3 classes, basically from starting from axial stress, allowable axial stress, bending stress, and then the hoop. So, all of them together I have just put it in here in each cell, and what is to be noted here, you just look at this column onwards, KL by R. You can see here most of the KL by R is less than typically about 80, and that is what we were talking about. Primary structure we try to keep the KL by R less than 80, and then you look at the weight starting from 400 kg all the way up to 1800 kg. So, the next one is the buoyancy, and the third one is the ratio of buoyancy to the weight. See, ultimately what we are looking at, any structure which has got heavier than the buoyancy or the weight is more than the buoyancy is not very good, because ultimately you end up you have to provide additional buoyancy for the structure to be floating during the installations time. So, as long as if you at least make the buoyancy to weight ratio is equal to 1, then at least the weight itself is self sufficient for the buoyancy, additional buoyancy requirements will be smaller. So, the primary purpose is to make sure that you come up with reduced weight, number 1, for the same answer. Basically weight means cost and weight means also additional buoyancy, at the same time satisfying other conditions like KL by R and D by T ratio. Remember, D by T ratio is a concern whenever you design a primary structure, you cannot have a larger D by T ratio, because you do not want the buckling to govern the design. So, looking at those things in your mind, look at the weight and buoyancy, and at the same time calculate all the stresses in the line, and finally conclude whether the unity check ratio is less than 1. So, you have a multiple, actually you have multiple targets to satisfy. That is why sometimes we call it this design optimization cannot be a single parameter optimization. You may have a multiple goals, but then you cannot find a single answer that satisfy all of them. You may have different answers depending on which parameter is a primary and which parameter is a secondary. So, you will just many of the commercial softwares are available for structural optimization, as long as you select the right parameters, put it in. So, it is a function of, for example, if you look at, you can write the equation of unity check as a function of several parameters. You can get maybe 10 or 15 parameters in the order of priority, you try to satisfy one by one. So, as long as you select the first parameter, whichever the first parameter you select for satisfaction, you will your answer will be different. So, basically you may get multiple answers, then you can write a goal. If you have say 3 or 4 answers, then you write a goal which I want to select, then you can. So, many of the optimization programs work on that basis, but of course, it's a simple one is the simplest spreadsheet that you can write yourself to make sure that your goal can be achieved. Basically, I think most of the time if you write your own code, you will understand what is exactly going on. The last one before we finish the discussion on the member design. See, whenever you have this hydrostatic pressure, it is always a problem. So, we try to not to increase the thickness of the member, instead many times this proves to be a alternative design by providing cylindrical or circular rings around the tubular members in order to prevent the waveform to develop, that means the local collapsing. You know why the local collapsing happens? Basically, local collapsing happens not just primarily due to hydrostatic pressure, but also due to the fabrication imperfections. You know, any one location you may have a small imperfection which can onset of buckling. Once that forms, then you will see that the next section starts to buckle. So, in order to prevent, you can see here what is being done. You can see we can either provide internal stiffening by means of a ring, just a plate, or you can have a external stiffening. This proves to be a economical solution than simply increasing the thickness by double. For example, 20 mm becomes 40 mm. Instead, you will realize once you do one calculation for a particular problem, then you will find increasing thickness is not an economical solution, because if you spread the steel that you have spent, for example, you take the steel and just spread between the two spacing, you will find it is maybe smaller steel compared to increasing the steel by few millimeter extra. So, what API suggests, you could provide this stiffening only for the hydrostatic pressure effect. It does not help in any other load transfer, especially axial and bending, it does not help, because it is only a discrete rings provided to prevent the local collapse. So, if you are thinking of applying axial load more, then you should actually increase the wall thickness. So, remember, the rings cannot help you in bending, rings cannot help you in axial stress, shear stress, because they are any direction, any location shear can happen. So, this is only to prevent. So, no, you should not get in your mind, I will provide rings, I can carry more axial load or bending. This is only for preventing the local collapse of the wall and purely for that purpose, and that does not help in any other form. So, the moment of inertia of the ring required to satisfy a certain conditions. Remember, when we did the FHE, so let me go back to this so called FHE. What was used here? When we calculated FHE, we have a geometric parameter called M, and that geometric parameter is proportional to the length of the member between supports, isn't it? So, based on that assumption, we have calculated the FHE. Now, we are going to calculate the moment of inertia of the rings required in proportion to what was the previously assumed the length between supports or the distance between the rings. Basically, it is so proportional to. So, if you have assumed the ring spacing is 5 meters, you calculated the FHE associated with 5 meter as the center to center of rings, and that stress will be calculated and used here, multiplied by the parameters mentioned here is L. In this case, L will become not the member length, it becomes the spacing between the rings, and d square divided by 80, all that you multiply, you get a moment of inertia of the section required, which is basically the section including some part of the cell itself. So, that is why I have put a little highlight, that you would realize the ring together with the part of the cell is behaving as a ring itself. So, the moment of inertia calculation is just simply do according to your second moment of area, you find out the neutral axis and then find out the moment of inertia about its own axis. So, basically that is why I have put so called XX, you see there, you simply calculate, as long as the provided moment of inertia is greater than the moment of inertia required by this calculation, then your assumption of 3 things is valid. You assumed a ring spacing of L while doing the member check, you know, FHE was assuming a spacing of L, and using that L you have come up with the moment of inertia, and that moment of inertia is satisfied by providing sufficient wall thickness of the web and the flange here. Using this formula, you calculate the actual moment of inertia provided and what is the moment of inertia required in this particular case. So, basically it goes back to the member check. As long as you assume 5 meter, you have to provide 5 meters as a spacing, but you should not stop there. You should provide the spacing 5 meter with the sufficient moment of inertia required, so that the rings will not fail. In some cases what happened, if you provide a ring which are just slender, you only have a one thing satisfied, spacing is satisfied, but the strength is not satisfied. So, instead of the ring satisfying or ring supporting the tubular will support the, because the rings are very long or wobbly. So, it will be hanging around, does not help the tubular itself, and that is why you need to proportion the ring stiffeners and their moment of inertia according to what is required by basically the allowable stress that you have calculated previously. The next thing is just a simple procedure. Basically, I have just listed down the ring spacing. What is perfect design is again very difficult to determine. You will come up with numerous number of combinations. For example, L was fixed say 5 meter. If somebody will fix L is 4 meter, you will get a different answer. So, you can see that for the same problem you will have many different answers, maybe 3 answers, 4 answers, 5 answers. Now, we need to fix a goal. What is our primary goal? Primary goal is to reduce the weight for sure, number 1. Number 2, you must make sure that it is workable. I can't have a ring spacing of every 50 millimeter, you will not be able to physically fit in. So, you will need to see whether it is possible to fabricate. So, half a meter, 1 meter, depending on what is the configuration you are using. So, these are the constraints you additionally put. The third thing, you have a cell wall thickness of 20 mm, you can't have a thickness of your stiffener 50 mm, you possibly cannot do a welding, because 20 mm with the 50 mm you will not be able to do the welding. So, you can see one by one you collect all the constraints, you put it there, the number of answers will come down to probably 1 or 2 maximum, and that is where you are going to be tested. Basically, you need to find the right answer given the constraints. So, if I give you a few constraints, you need to look at which one to be supposed to be used as a first priority, and then look for a right answer, and that is what the question that you are going to get tomorrow. It is not that simply you have all the equations and then I can simply take the calculator and substitute and answer is there. That secretary also can do, you do not need engineers to. So, the basic idea is the design means trying to find out the right answer for the given constraints. If the constraints are not given, everyone will come with different answer, and ultimately I may not be able to correct it. So, you will be given constraints in the real design also, many times you will get the actual constraints will be given, so that you can work out. I have given you 2 problems here. Basically, one is the design of a simple circular cylinder. I think most of you might have seen, if you had enough time to read it. It is just a collection of what we discussed over last 3-4 classes. Basically, all the information is given. In fact, this is a very simple problem. Verify a jacket brace of diameter 762 by some wall thickness, load is given, moments are given, and unbraced length is given, and the yield strength is given. So, it is a very simple forward problem. You do not need to do anything actually. You take the equations and just fill in the values and use your calculator, you will get the answer, is not it, because there is nothing else to be done. But only one thing you need to make sure understand, jacket brace. So, the word you need to note down, because you need to assume a reasonable K factor. So, you should not ask where is my K factor. So, basically the K factor table will be given if required. So, you need to understand the reading the words is very important, because you just have your answer there only. So, you read jacket brace is K factor is 0.9 or 0.8 depending on whichever the situation, and select that K factor, that is what I have taken, and then proceed with the simple procedure of trying to find out. So, this page you see so many formulas, you will not be given this formula for the exam purpose. Trying to find out the sectional properties of tubulars, I am sure for every engineer you need to keep it in your mind, is not it. So, you do not ask how to calculate the moment of inertia of tubular section. In here this formula is little complicated, there is no reason why you should memorize. So, the allowable bending stress, allowable axial stress, the formulas will be given in the back side of the question paper. So, you do not really need to worry about it. So, basically you see here allowable bending stress is directly dependent on the d by t ratio. So, you calculate the allowable stress, and then we have the allowable axial stress. Prior to allowable axial stress, you need to calculate the whether to verify whether the member is local buckling is having effect or not. So, what I have done is I have just taken the procedure from API, assume the local buckling coefficient, find out elastic buckling stress and find out inelastic local buckling stress, and compare this with the yield stress. If it is less than the yield stress, then that will be taken. In this particular case, I think local buckling is not at all governing, because the d by t ratio is quite good, and basically find out the limiting slenderness ratio, which was again you see here at the bottom in the formula it may not be there, but in here I have selected to put the comparison between the buckling stress and the yield stress, so that I can take, if the buckling stress is smaller, then automatically will be taken, and then calculate the allowable stress after this, which comes to be 166, and then you go for applied stresses. I think you have the applied axial stress, area divided by load divided by area, and then computed bending stress for x and y directions or y and z directions. Sometimes you may have x and y depending on axis systems, and then you find out the three unity check formulas. The fourth one not required, because here it is a symmetric section, we do not have the fourth one, and simply find out what is the. So, automatically here we have a computer code decides, but when you are doing calculations one by one, you have to just do it and then take the highest ratio, that will be the governing case, do not take the smallest one and then provide. So, this type of problem is very easy to do, because there is nothing else to think. What you need is take the formula and feed the values, you will get the answer. You understand the idea, no? So, if I give you, I think at the end of these slides I have given 5 problems. If you had time, you should have practiced. So, basically the next problem is the design of an internal ring stiffener for a buoyancy tank. You know, buoyancy tank, I think we have seen some pictures, I think in the early days of introduction. Basically buoyancy tanks are large diameter tanks attached to the jacket, so that the jacket will float in case if the jacket does not have enough buoyancy. Basically we fit it in, and then we can remove them at a later stage when it is not required, because after the piling is done. That means the primary purpose, you must understand, is not load transfer. The primary purpose is to hold this basically the air inside without any break or buckling. There is no axial load, no bending load going to come here, because it is just a sacrificial tank fitted onto the structure, it is not going to carry any load. That means here we are not going to have any interaction between axial load, bending load, or here only purely hydrostatic pressure. That means the problem becomes very simple. So, in this particular case, you are given a diameter of 2000 millimeters, 2 meters, quite big, 15 millimeter wall thickness, hydrostatic pressure of 100 meter water depth. So, you can see it is quite deep, and then the spacing of rings is supposed to be 2 meter, you should not go less than 2 meter, and you can see from this number 15 millimeter is given. You can't have a stiffener thickness greater than 15. I think if you have studied, or probably I will explain one of the days, when you are trying to weld a thicker plate to thinner plate, the thinner plate will burn away during the heating process. So, you cannot have the second plate which is going to be welded bigger than the parent plate, typically practically not possible to weld. So, you could see that you should have the stiffener less than 15 mm, and then the yield strength is already given. You can't select a yield strength of 340, 350, because you have no choice. So, see, 3 or 4 constraints are given. Now, you have only 2 choices. You either can have a ring only, something like this, without the flange. You see here, this is the flange, this is a web, this is the cell which is behaving as a part of the flange, another flange. So, you have 2 choices, either you can have this web only, or if not sufficient, you can provide additional flange. Now, this web, you are very much constrained by the thickness. If you have a 15 mm parent thickness, the web also can be maximum 15 millimeter. The outstand, how much we can go, if it is too big also no use. So, we need to look at the slenderness of that, basically that will be the guidance we need to look at. So, if you look at the d by t ratio of the pipe is 133, it is quite large. You know, normally for structural members we have about 60, less than 60. So, this is definitely larger than 60. So, it goes into a cylinder range, surely we need to provide rings, and you have the spacing given to you as 2 meter. So, simply calculate your hydrostatic pressure and applied hoop stress, basically P d by 2 T, which is 68 megapascal, and then find out the geometric parameter, which I think we discussed earlier in this morning, and find out the coefficient of buckling, basically using this 5 stage formula. As long as you know where is the m value, you do not need to check every one of them. By looking at that formula, you can see where I am going to fall in. You do not need to do every one of them and then finally decide, is not it? As long as you know the value of m, you can straight away go where the value of m is going to be. So, maybe here or maybe here, then use that formula to calculate the, when you are doing your problem solving in the exam, do not have to go through every one of them, there will not be enough time. And then you find out all your elastic hoop buckling and the inelastic or critical hoop buckling, and then use the factor of safety of 2, because there is no other load, only pure hydrostatic, and simply find out the unity check, which is 0.99, is not it. Now, what we have done is we have assumed that rings are provided at 2 meter, and we have designed the tubular section, which will be very safe. But what we now need to see is whether the 2 meter what stiffener is required. If you stop here, is only half answer is there, the remainder has not been done. So, for that 2 meter, you have to go and look at the stiffener design, because we have assumed that every 2 meter the cylinder is stiffened by rings which are capable of taking the buckling loads. So, that is what we are now just going to do, find out what is the moment of inertia required, and then start assuming, and this is where if you assume 10 mm for example, typically I have taken 15 mm and I have just come up with 150 mm outstand, which typically any unstiffened element, more the plate thickness to width ratio should be somewhere around 10. We will talk about this when we are talking about another code called the American Institute of Steel Construction, ASE code. So, typically if you have 100 mm, 10 mm minimum thickness, if it is 150 mm, you should have minimum also 10 mm. So, in this particular case I have just taken 15 mm and basically kept the outstand or so called the web height as 150 mm, and I calculated the moment of inertia using the neutral axis and stuff. So, I find that the moment of inertia provided is 1.287, whereas the moment of inertia required is about 1.05. So, provided is higher. So, I am satisfying the requirements. So, basically the stiffener design is nothing but providing sufficient inertia to take the bending loads coming from the hoop.